Thank you very much. Thank you for inviting me. It's, of course, a tremendous honor and a pleasure, and great to see many friends. When we chose this date, it was Brexit. I realized afterwards it was Brexit today, but that was postponed, but not Halloween. So anybody who wants to leave because they want to go trick or treat, it's probably a good idea. I will not feel offended. I never met Ahlfors, but of course his writings and books influenced me greatly. His book on complex analysis is by far the best book, and I say that I have to be very careful because at Princeton we teach out of somebody else's book. But when I teach out of Ahlfors's book, and people look at me like you're not loyal. It is by far the best book on complex analysis if you compare it, say, to Titchmarsh's book, where analytic function is a power series, and that's what you think of as analytic function. There's no geometry associated with it. The book by Ahlfors called Conformal Invariance is actually, I think, a little less known. It's another beautiful book which, as a graduate student, I learned many things, like covering spaces, topology, and things that might come up here. There's one chapter missing from that book. He introduces a method to prove the Bieberbach conjecture called Leibniz method, and he does a special case. And there is a proof now, of the branch proved the conjecture, but if you apply Leibniz method to something called the Milin-Lebedev inequality, a slightly more complicated version, then everything flows, and there's a one-page proof by a fellow called Weinstein. And if anybody ever reproduces that book, they could complete the book beautifully with a complete proof of the Bieberbach included. So if any of you are in control of reprinting that, I urge you to get someone to include that. It's really a beautiful book. Research-wise, Ralph Phillips and I, many years ago, were learning how to vary complex structure and then study some tricky spectral problem. And we needed to compute second derivatives in these Ahlfors Bayes deformations, and we couldn't do it. And sometimes you go to a conference and it makes a big difference for young people. Let me encourage you to do that. I went to this conference. It was Mostow's 60th birthday. That fellow there, one of the Yaos was there, and Sue was there. Many people were there, and we were trying to compute this. This was on my mind. And I ran into a fellow called Scott Walpert, who was also there, and he said, you know what you're trying to compute, I'm pretty sure it's in a paper of Ahlfors. Let's go to the math library. He immediately took me to the math library at Yale. We looked it up. It's exactly what I needed, the technique. And on the train ride from there, I used to be at NYU at the time, back, I did by far the most pleasurable calculation I've ever done in my life. By the time I got off that train, I knew that the answer was an L function. And that was, I couldn't dream of anything better. So that's about as much as I'll say of Ahlfors, who was a great complex analyst, great mathematician, and of course developed Neven-Lina theory beautifully. The talk that I'm giving here today is it's a problem that was formulated by Lang. I'm going to explain it and its solution, and which over many years I've found it solves many problems, and it should be better known. And so I'll review some problems that it solves that are outside. So the second half of this lecture will be about applications. The first half will remind you what the actual conjecture is and what goes into its proof. And I will spend the last 20 minutes on a completely new application, which uses the hardest part of the theory, which to me was quite surprising. All right, so let me tell you what this Lang's GM conjecture is. It comes in two flavors. This is not usually how it's presented, but I have always thought of something called vertical and something called horizontal, and I want to explain what I mean by that. So the setting is a torus, which is just the complex numbers to the nth power. You might it might be disconnected, but let's not worry about that. So these conjectures go by Lang's GM. GM stands for the multiplicative group, but it's a torus, complex torus. And we have a subvariety. We don't even say what field of definition. we have a subvariety of the torus given by zero sets of, say, Laurent polynomials inside the torus. An example, a very easy example, would be this polynomial, the zero set of that polynomial, which is the sum of z plus z inverse with each coordinate equal to 0. That will be a critical case in one of the applications. And for the vertical part, the most important question that we're going to ask are about the points of finite order in this group. So this is an abelian group, an algebraic group. It's abelian, and it's got points, the roots of unity, points, all of whose coordinates are roots of unity, the torsion points of the torus. And we're interested in the torsion points of the torus which lie on a subvariety. That's what this conjecture is about. That's the vertical conjecture. So given V as above any algebraic set, the conjecture that he made is there are finitely many subtori, or translations of those by torsion points, finitely many, such that the intersection of the torsion points in the torus with this V is already the intersection of the torus points, the torsion points with these subgroups. And these V's are contained, these T's, are contained in V, and you can find them. So a seemingly complicated nonlinear problem of the intersection of these torsion points with some complicated equations is actually linear. That's rather striking. And he conjectured this, and if you look at his book on Diophantine geometry, I think Tate, Serre, and Ihara gave him a proof of this in the case of a product of two in C star cross C star. And I'm sure if they thought about it, they would have been able to do it in general. I got interested in this and needed it for one application, so I found a general proof, and I'm going to say a word about that proof in a minute. Let me emphasize that if the sum of these subtori could be points themselves, in which case they're torsion points. So if there are no subtori, then it says that the torsion points intersect the subvariety just consists of finitely many points. So it's a finite statement, and those points are torsion. Okay, as I say, there are many proofs of this vertical one, and let me give you the worst proof. It's the proof that I've found first, but often, this is a lesson you learn when you get old, often something that's not natural actually is much more general. So this proof generalizes in a way I want to explain to you, and it's actually become rather useful. So the proof goes like this. Let me just do the case of 2. So we're looking at torus, which is C star cross C star, but we're looking at roots of unity, so I'm only interested in the points in S1 cross S1. And the torsion points, let's take a torsion point, zeta1, zeta2. That means that some power m1 of zeta1 and some power m2 of zeta2 is 1. Now, if I look at whatever the defining equation of the subvariety V, which in this case would be like the zero set of a trigonometric polynomial with some coefficients, the coefficients lie in some field. Let me call that field K. And let me look now at the Galois group of the extension where I add these torsion points, these roots of unity, to the field K. Now, the reason this problem is quite easy compared to what I'm about to show you in a minute is that basically, if the order of a torsion point is large, then because the degree of the cyclotomic field, Q zeta m over Q, is what's called the Euler-Phi function. And the Euler-Phi function is almost as large as m. It's bigger than m to the 1 minus epsilon for every epsilon. It means that this Galois group is very big. So suppose I want to prove to you that in the case that that curve there that's drawn there, the V, contains no line segments in this exponential variable, in this torus, so drawn as it is over there. Suppose I want to prove to you that there can't be points of torsion points lying on that whose order is bigger than some very large number. And the reason for that will be is if there is such a torsion point, then the Galois image of that point will also be on the curve. That's how I chose that field. And so then, and since this orbit's big, I'll have many points. So if I could separately give you an upper bound, which is better than m to the 1 minus epsilon, or let's say it's m to the half or m to the delta, where delta is 1/20th, then I get a contradiction. So there's the big tension between the size of this Galois orbit, and giving a non-trivial upper bound. Now, I only need a really easy upper bound here. I mean, if I'm a straight line, the number of torsion points that'll be on it, if you think about it for a second, will be about m. So if I'm curved, I should be able to gain an exponent. And there's an amazing argument, which is what's at the heart of all the generalizations. It goes back to Jarnac. Let me give it to you. That's this little thing at the bottom there. Suppose I have a convex curve in the plane, actually, continuous convex curve in the plane. This is real analysis with one derivative, let's say. I have a convex curve, and its length is L. How many integer points can it have? Points with integer coordinates, both coordinates are integer. Well, if it's a straight line, there could be L of them. But if it's strictly convex, it's at most L to the 2/3, and that's sharp. And the reason is, if I have 3 points, consecutive points on the curve, I draw them, and then I'd make the triangle between them. They've got integer entries. By Heron's formula, the area of that triangle is not, firstly, they're not a straight line, so the area is not 0. And by Heron's formula for the area, it's at least 1/2. That's one of the main arguments in many of these things. That number, integer which is not 0, is at least 1. So it's at least 1/2. So that if the 2 points are very close, the third point has to be very far away in order to accommodate that. And that gets down to L to the 2/3, and that's sharp. And then you can think, all right, well, maybe if I take 4 points and form a cleverer thing than this triangle, maybe a Wronskian, and you can get down all the way up to L to the 1/2, and this was done by Swinnett and Dyer, and he stopped there. But actually, if you remove algebraic curves, you should go all the way down to L to the epsilon and get the sharp bound, and that was done. So this actually can be generalized, and given that, you can push it through. It's much more complicated in higher dimensions, but you can give a proof of Lang's GM, the vertical version. As I said, this proof, there were a number of proofs, but this proof actually has turned out to be, in hindsight, to be quite useful. Firstly, Bombieri and Peeler proved this statement that I just outlined to you. It's a problem in sort of transcendence, mean value theorem, elementary. All these things are elementary. Doesn't mean easy. Elementary means usually hard, but it's elementary means you don't use anything fancy. And they prove the following theorem, that if you have a transcendental curve in the plane, and you look at all the rational points in a compact part of that curve, then the number of rational points of height less than x will be at most x to the epsilon. Sharp. There are very few sharp bounds of this type, and that was a beautiful pushing of this idea. And Peeler then wanted to generalize this to higher dimensions. It took him another 10 years, and eventually Peeler and Wilkie proved this amazing theorem, which gives a sharp upper bound for rational points on the transcendental part of any O-minimal structure that you can define in real geometry. So it would be a higher dimensional generalization. The trouble when you try to generalize this to higher dimensions and you want to do something inductive and you project, you get out of the class of real analytic sets and you get to the class of definable sets by real polynomials. That has a quantify elimination theory, that's due to Tarski. Van den Dries understood that you could do something fancier and add other functions like exponential, and that's a natural setting in which you have quantify elimination. And Peeler and Wilkie prove a sharp upper bound, which is the source of many of the further results here. Using that, Peeler and Zanier then proved the abelian variety version of this Lang's GM. That is that in an abelian variety, all the torsion points lie on finitely many abelian subvarieties, or translates thereof. And that was proved by other methods also, but the breakthrough was this is the only method known today to prove the André-Oort conjecture for products of curves. That was done by Peeler by using this tension, using his upper bound with Wilkie, and you needed a lower bound on Galois orbits. That, in the case of product of curves, follows from standard things, but in higher, for AG, that was provided by Zimmermann as all the transcendence ingredients that are needed. And these two fellows have proved the André-Oort for AG by this technique. It's nowhere as easy as on the torus that I started off with, but the general approach is exactly that. So this is one direction, which I don't know too many applications outside of number theory. I'm going to show you applications that have nothing to do with number theory, at least on the face of it. All right, now let me tell you about the deep side of the subject, the horizontal. That was vertical. Much harder is horizontal. This lies much deeper. It goes back to works of Thur, Siegel, Roth, and most importantly, Wolfgang Schmidt. So let me state the conjecture and and it's actually proved. So suppose I have a subvariety of the torus, just as we started before, but we don't look at torsion points. We now take a finitely generated subgroup. So I take a finite number of elements in the torus, and I take the group generated by them. I call this horizontal because this might be a unit group in a number field, so it might be units lying on V. But this theorem is group theory, so you take a finitely generated subgroup, and you ask, and that finitely generated subgroup could have very many elements, and you ask, it's a billion, but could have infinitely many elements, and you intersect gamma, the finitely generated subgroup, with V. And then again, this is a linear problem. You can find, given V, you can find, I say you can find, this is not effective, this is very deep, but there are finitely many subtori. The number nu is always, I'm using nu, it changes from problem to problem, obviously. There are finitely many subtori, or translates of subtori, such that, which are contained in V, and such that gamma intersect V, this horizontal group, is the same as gamma intersect that unit. So it's again a very complicated problem, but the structure is purely linear. The number of tori that are in the theorem can be made effective, but not in this proof or any proof I know, to find the actual, say there's a zero-dimensional tori, to actually find them. This was proved by Michel Laurent in the 80s. It's a great theorem, and the key, he reduced it beautifully to this versions of this Schmidt subspace theorem, which is really the heavy lifter in this subject. And it's the first and breakthrough result in doing higher dimensional Diophantine finiteness theorems. And the theorem is very easy to state. It's proved, it's an ingenious extension of the work of Roth. Suppose I have n linear forms in n variables and n of them, with coefficients lying in an algebraic number field, say real, so that everything's real here. And I look at the product of the linear forms and I ask how often for x in Zn is the product less than x to the minus epsilon. So epsilon is a parameter that you give yourself, and you ask how often is the product of these numbers less than x to the epsilon. The norm is the ordinary, any Euclidean norm. And his amazing theorem is that all solutions to this lie in a finite number of proper Q subspaces. That should sound like Roth's theorem if you've ever seen it. It's a higher dimensional version of it, and it's one of the deepest theorems in the subject, maybe the deepest theorem, only majorized by Folting's theorem, which is the same statement in an abelian variety, about subvarieties of abelian varieties, which is a nonlinear version of this. Without this, I don't think the other one could have been formulated. Let me emphasize again in applications that the number of subspaces can be bounded, but finding them is not effective. You might ask, well, where does non-effectivity come in this? It's always the same reason. This was Siegel. Anything Siegel touched, you knew it's hard, and because it's hard, this feature came. So what you really prove, say in the case that the subspace, one dimension, it would be points, which is in Roth's theorem or Thur's theorem, you really prove that there are at most 10 points, and that 10 depends on the data. If they find 10, there isn't an 11th. But you never find more than one. So you just don't know where the others are. So if you have something very weird, you show it can't happen again. But unless you find that weird thing, you don't know how to bound the size of the solution. So you can't find it in principle. And that's a sign and that's why we so worried about effectivity in this, because you might say, well, what did you really prove? But this is a remarkable statement that there are only finitely many Q subspaces. So this is the workhorse, and Michel reduced it to that, Michel Laurent. And now there's even a version that Lang formed, which is both vertical and horizontal, and in this third application that I'm going to talk about, I need both. So let me state this. And I need it in this amazing uniformity version. At least I do in this Or we do, me and my coworkers, you'll see. So one way of combining vertical and horizontal is, let's take the division group. Lang did this. So you take all elements whose powers, non-trivial power, lies in the group, and you call that gamma bar. That's the division group of gamma. And then you can say, maybe everything's true if gamma that's finitely generated, and gamma bar intersect V already has these finitely many subtori, or translates. So if you take the group 1, its division group is the torsion point, so that's your vertical one. And now I'm taking a finitely generated group and doing the same thing, so it's clearly vertical and horizontal. And that's also proved, and I'll give you the best result known, which is completely uniform and extremely useful and friendly to use. The proof's very difficult, but the statement is user-friendly. So you have a subvariety of C to the n, and gamma finitely generated. Let's say it's of rank R. I'm even going to give you the dependence of the number of subtori. Then there are subtori contained in V. You always have to find those. As I say, you can't find them, but you can bound their number in the situation, such that the division group intersect V is already the division group intersect those. And the big new thing here is that the number of tori is at most some constant that you can write down that depends on the variety V and depends on the rank with this power R. So that's a uniform statement. There's no number field there. I'll say a word about the proof in a second. So CV can be determined, but in principle, I don't know how to find the T's. Often you can find the T's if the geometry of the problem is such that maybe the variety V itself is a torus, subtorus. I'm going to explain that in a second. All right, so the proof involves specialization and reducing to the situation where the finitely generated group has coefficients in Q bar. Then you can start to use serious theory of heights. And there's a notion of an absolute height, which Schlichterwey developed beautifully for this and others. And the inequality that is the key input that Schmidt uses can be proved in this absolute height, which means you measure the height of a point, no matter which number field it lives in, scales properly, and you get completely uniform statements about the number of tori. And that's a remarkable theorem. Now, the deep part is this, there are only finitely many. So when the points have very large height in any natural way of defining height, then you have to use this very serious theorem of Schmidt to get control. But to make a uniform statement like this, you also need to control the number of small points, and that's a completely different game in the geometry of numbers, and Schmidt happens to be also the king of that too, so this is done with Schmidt. But Everts and Schlichterwey have played a very important role. Much of it is reduced to this case where V is this by using coordinates which linearize the problem. So once you have control of this with all tori, so this is kind of the main test case. Okay, I've got to the first part of the talk, which is what the statement of Lang's GM is, and given you that in the vertical case, it's still very active. In the horizontal case, this has been known for some number of years. So now I'm going to give you 3 applications. So the first one will be about topology. Let's look at Betti numbers in abelian coverings. So suppose I have a topological space or a complex, CW complex. I'll look at the fundamental group. I'll call it pi1, as everybody does, and I'll look at the first homology group, which I'll assume is infinite because I want to make abelian covers. First, unramified abelian covers. So I have the Hurwitz map from pi1 to h1, and then h1x z, I'm using z coefficients. I will look at the maximal nth abelian covers. I just go from z to z mod nz. So the thing on the right-hand side is a finite abelian group. Let rho n be the composition, and the kernel is a finite index subgroup of pi1, and pi1 over this kernel is that abelian group. So I construct in this way, purely with a group and the starting space, this abelian cover, which I'm calling the unramified part, the yn. And you can ask how the topology of yn depends on n. Many people have asked this, and I'm going to look at one specific example in a second. Well, if you have coverings which are unramified, any Euler characteristic Chern numbers, they all multiply. They behave beautifully in covers. But Betti numbers, they don't want to behave beautifully. They are even called, I think by Zariski, irregularities in the case of surfaces that I'll turn to, because they don't seem to want to behave nicely. But the moral is, of course, they behave nicely in abelian covers. That's what this Lang GM tells us. That's the point. So for this simple part of the unramified covers, I'll show you how you reduce that to Lang GM in a moment. But the answer is that any Betti number or any topological invariant that's given in that kind of information is polynomial periodic in N. So that means that there's a separate number Q such that on progressions modulo Q, these functions are polynomial functions. So you should think of this as a generalization of an arithmetic progression. People love periodicity theorems for topology. This is an example. The key word here is abelian. If I drop the word abelian, I have no idea how these things behave, and they are really irregular. But in the abelian covers, they are very regular, and the linearization, the regularity, all comes from Lang's GM. If you normalize these unramified covers and resolve them, maybe take a minimal resolution, then this becomes very interesting in many, many cases, including a case that was very popular many years ago, studied by Zariski in his theorem of covering planes, Herzebruck, Livner, and most importantly, the theorem I want to describe here by Eko Hironaka, who happens to be here. I'm very happy to see you. So take a complex surface and take finite number of irreducible curves, distinct curves. There's some other conditions put on, but let's set it up like this. And let's take x minus c. You could think of the curves being even straight lines. That's the case that many people studied. So C is the union of the curves. Take x minus c, and take this unramified cover yn, and normalize it. I'm going to be interested in the Betti number. It doesn't matter how you normalize it. So you take some resolution, and you'll get these surfaces, complex surfaces y and tilde. And how do they depend on n? Well, they are anyway very interesting because many of them are of general type and satisfy and can be made with careful choices, even with straight lines. This is what Herzebruck did, to satisfy the Bogomolov-Miyaoka-Yau inequality. The inequality that if it's sharp, then Yau proved that you're covered by the ball. But how do you make examples that are sharp? Well, maybe you can, I'm just explaining to you that this really gives you a nice geography of surfaces because you can make those and many, many others. But how do the irregularities behave here? And I think when I first met Eko, there were programs. She had a way of computing these, as did Herzebruck students. Turns out they're polynomial periodic. Once you know what that is, you look at the data and you see it, and she proved it, and it's a beautiful example. When you normalize them, it's quite a bit more difficult, but still Lang's GM is a savior. So the way I would say it is irregularities are not so irregular as long as you're in an abelian cover. How do you reduce it? Well, and this is where the torus comes in. You look at all characters of H1 into the complex numbers. So H1Z is an abelian group. It's got some rank and it's got some torsion. You look at all the characters into C star. Let's just forget the torsion. It's a torus. And then you look at the jump loci. You look at the places as a function of the character of this twisting where the local twisted homology, maybe you have a line bundle, you're twisted by one of these guys, and you look at the dimension of the homology. This is a semi-continuous function. You look where it jumps. The places where it jumps is an algebraic subvariety. There are many ways of seeing that. And the places where it jumps by 2. So if you want to actually go compute the numbers that we're about to compute, you face these intersection, as I'll explain in a second. But let me just say a word about the way Eko did this. She used Fox calculus and something called the Alexander polynomial associated with Fox calculus to do this explicitly. It's not difficult to see these algebraic, but you can turn it, you actually write a program and it computes these things. These things are not in the general setting sub-tori themselves. They could be complicated. The jump loci could be very complicated. But Lang's GM comes in because what you're really interested in when you're looking at the abelian cover, what we called y and tilde, you have to understand the jump loci and the normalization loci. Those two are given by algebraic sets, and then you're intersecting all the division points with the set. Looks complicated, but Lang GM says you can replace the set by straight line, by subspaces, and then if you unparse that, that will give you polynomial periodicity. So that's Echo's theorem. In many of these algebro-geometric cases, since that work was done, people found, most notably Carlos Simpson, that if you're in an algebro-geometric setting of line bundles, say maybe in projective space with a complement with some properties about crossings, that the actual subvariety, the actual jump loci, are sub Tori themselves. So once you know that, you don't need Lang, because you only jump on a very structured set. In general, for this problem, you could jump anywhere, but that's a quite deep theorem. And I should say that the proof by Simpson of this uses some transcendence methods. And theorem, modern proofs use Axe-Shanuel, which is a transcendence method, which of course was also present in Pila Zimmermann's work. There is something transcendental about trying to understand this kind of problem when it's a defined structure. So that's application one. Let me the second one is an even simpler application. It's to classify, all right, how am I doing? Let me go to application 3 first and then come back to application 2, if that's okay. In application 3, I have a nice story about Xingtang Yao, as I'll explain now. So this is a case where I'm going to use horizontal and vertical, and it's about quantum graphs or metric graphs. So this is going to be everything in one dimension, and looks like it has to be, what can you say in one dimension? So let me start with the unique one-dimensional compact Riemannian manifold. That's a circle. There's only one parameter, the length. That's my story about Yao. He was a professor when I was a student at Stanford many years ago, and I went to his lectures. And I got interested in spectral theory of Riemannian manifolds. And at some point, I was looking at vibrating strings, and I had a whole bunch of theorems, but then I kind of converted them into a metric version, and I said to him, I've got these amazing theorems about a one-dimensional Riemannian manifold. And he said, but that's the circle. I said, oh. And I left. Okay, now I'm back here. The theorems were all true, but it wasn't big. It was kind of trivial. So I'm going to make the one-dimensional manifold allow it to have a finite number of singularities, and now I'm back to answer my question. I'm back with a vengeance. All this is joint work with Pavel Kurasov, who's a guy who works on what are called quantum graphs, which I'm going to define in a second. But just going back to the circle for a second, we're interested in one dimension, so we don't need to talk anything fancy like Laplacian. It's just d2 by dx squared on, you take the unique parameter, uniformizing the length. And the when I talk about the spectrum, I'm going to do the way a physicist would do it. You write the eigenvalue equation as Laplacian phi plus k squared times phi, and I'll take k and minus k because I'm going to be looking very carefully at the structure of the spectrum of this one-dimensional manifold that we'll be looking at. But if it's the circle, then the eigenfunctions are e to the 2 pi I mx, and so the k's are just an arithmetic progression. So the spectrum of a circle of length L up to the parameter L is just an arithmetic progression. We'll be interested in the Fourier transform. This is something that people study in the nature of the spectrum here. The Fourier transform of putting delta masses at the spectrum and ask, what is the Fourier transform? That's a tempered distribution. What does the Fourier transform look like? And if there's one formula that I would not be able to move without, it's called the Poisson summation formula. It's the heart of many, many things. It's the statement in this setting that the Fourier transform of the spectral measure, which is the sum of delta masses at the spectrum, is itself a sum of delta masses at the dual lattice. So it's also an arithmetic progression. And if you're a micro-local analyst, you treat the Fourier transform as a trace of the square root of the Laplacian times Xi. And the remarkable thing here is one can, in general, understand the singularities of that in Xi But the remarkable thing in certain manifolds, and very few, locally symmetric spaces, and something like the circle here, which is a locally symmetric space, the transform is a sum of delta masses. These have been studied. If you have a measure which is a sum of delta masses and its Fourier transform is a sum of delta masses, Yves Meyer calls this a crystalline measure, and it's become quite a popular subject. And I'll return to that in a second. All right, so I'm now going to allow, if Professor Yao will allow me to have singularities in my one-dimensional manifold. So this is what is a metric graph or a quantum graph that is a very active area as a toy model for quantum chaos, and I don't know why, because it's not a good toy model, unless you make the graph get very complicated. So you may as well be looking at graphs. But once you want to have an infinite spectrum, this is a very interesting question. So I'll introduce a finite number of singularities by drawing a graph like that. And the vertices are singular, so I'll have to tell you what boundary conditions I'm putting for the second-order operator. And there are different boundary conditions that one can choose here, which will lead to a similar theory. I'll choose the simplest, which is called Neumann, or free boundary conditions. So on the edges of the graph, so the graph is some finite graph, on the edges of the graph, the eigenfunctions are just of d2 by dx squared. In that parameter, they're just exponentials, e to the I x and e to the minus I x. But in order to make the boundary conditions meet, there's going to be some non-trivial entire function which measures the spectrum, as you'll see in a second. So the boundary conditions I'm putting on these Neumann boundary conditions that the function phi, an eigenfunction, should be continuous on this metric graph, or forget about quantum graph. That's just a synonym. And I want the first derivative to be continuous at each vertex. So if I take the derivative of all in a directional derivative coming into any vertex, the sum of that should be 0. So the function's continuous, and the first derivative is trying to be continuous. So if there's any vertex which is degree 2, like this v here, then if the function is an eigenfunction and the first derivative, because this is a second-order equation, that will not feel such a singularity. So I'll assume, and this is very important, that there are no vertices of degree 2, because you can just throw them away. And if there's a vertex of degree 1 just at the end, that means that the derivative of the function must be 0 there, and that's why it's called Neumann boundary condition. And those are the boundary conditions, and that also defines the self-adjoint operator whose spectrum we're interested in. So we got the second-order Laplacian on a quantum graph, and I want to compute its spectrum. And as I say, you will see if you just search quantum graphs, you'll see millions and millions of papers of numerical computations and all sorts of things. I'm going to do something very important here to make all my formulae exact. I'm going to throw in at the eigenvalue 0, basically the Euler characteristic. So the multiplicity of 0 will not be 1, which it is if the graph's connected, as I'm assuming. But I will make it by force to be 2 plus a number of edges. Capital N will be the number of edges. M will be the number of vertices. That's a fixed number, so you don't have to worry about that. All right, you've seen the circle. The spectrum was an arithmetic progression. Now, let's take the second most complicated thing, a figure 8 graph with lengths L1, L2. To make the metric graph, I have these two parameters, L1 and L2. The spectrum of that can be computed, you'll see in a second why, and it happens to be a union with multiplicity of 3 arithmetic progressions. I'm highlighting this because it's the only guy that ever has this property. This is the last guy with that property. It's very special. So this figure 8 has that spectrum. It's a union of arithmetic progressions. So if I took the measure and took the Fourier transform, it would also be a union of arithmetic progressions. And those are the boring crystalline measures. You're going to see every other one of these gives a fantastically exotic crystalline measure. When you are in one dimension, nobody's impressed with a Weyl law, but you can prove it here, that the number of, so the spectrum now is a set of real numbers. It's symmetric about the origin. Its density is roughly that of an arithmetic progression, because it intersect the interval minus tt, if t is large, will be a constant which depends on the lengths, times t as it would in one dimension, and the remainder term is at most 1, just like it would be if you were in arithmetic progression. The number of integers up to t is t plus 01. And just how much is left over is the fractional part is a subtle function. Here, I'm not going to study that. That's quite subtle. All right, so it looks like an arithmetic progression, and people have wondered what these things are, and I'm going to answer that for you now. But I want to first show you how to compute it and where torus comes and where algebraic subvariety comes and Lang's GM comes in its strongest form. So the eigenfunctions are exponentials like that on each edge. At the endpoints, I have to match some boundary conditions, and it's convenient to introduce what they like to call the scattering operator. So I'll introduce n variables. They're going to be my toral variables, z1 to zn. And this will be a 2n by, n is the number of edges. I'll make a 2n by 2n matrix whose entries are, or depending on these z's. So the U is a unitary, not unitary, sorry, it depends on the z's. U is this matrix which depends on z, which is 0 unless, so remember now I'm going to make 2n by 2n. So I'll take the edges e1 to en, and e1 hat is the same edge going backwards. So I've got 2n oriented edges. And if you give me an f and a g, which are oriented edges, if g follows f, so that's, if f equals g, that's ordinary delta function, I multiply that by zf, and I put that in this diagonal matrix. This diagonal matrix, U, has got z's in it, and it's several variables. The scattering matrix, which is the thing that if you sit down and write down the linear algebra which matches the boundary conditions, is a matrix which is again indexed by the oriented edges. And if f follows g, then the entry is non-zero. It's minus the delta function of f g hat. So if f follows g in orientation, plus, and this is very important, there's something quite deep that's involved here, as you'll see in a second, plus 2 over the degree of the vertex which f and g traverse. So that is the entry in that position, and it's 0 otherwise. And it's not difficult to check, and this is extremely important, that the scattering matrix is unitary, and it doesn't depend on z. And this whole theory will work if you put other boundary conditions with that property. All right, now you write down the following polynomial in several variables, which is going to be our 0 set that we'll be interested in. And you take the determinant, so it's the secular polynomial, but this is not the characteristic polynomial of any given matrix. This is really a function of several variables. Det I minus u, the dependence on z is there, and S is this unitary matrix. It's a Laurent polynomial. And it can be used, as I'll show in a second, to compute the spectrum, and that'll be the way we proceed. From the very definition here, and this is important, there are some properties of P. The first property of P is if I, it's degree 2 in each variable separately. It's degree 2n totally, but it's degree 2 in each variable. That's just because there are two z's. There's f and g. There's zf with f and g, and those are oriented edges, so it's counted twice. Much more important property is that these polynomials are what are called stable. The unit disk stable. This is in the theory of hyperbolic or stability polynomials. This follows immediately from the unitarity, but it's critical to everything we do from here on. So what stable means is I have this Laurent polynomial in several variables. I'll say it's stable if when all the z's are in absolute value less than 1, p never vanishes. And not only is p stable, but if I invert the z's individually, that's what p iota is, that's also stable. Both of those follow immediately from the unitarity. So these polynomials have no roots where all the variables are less than 1 or all the variables are bigger than 1. So it means that the roots somehow have been forced onto a circle. This is going to be very important as for the Fourier transform to somehow be a tempered distribution on the line, something that won't be obvious from a formula that I'm going to write for you. And then this was known, I think, before, but it's clear in this paper of Barra and Gaspard from about 2000, that you can compute the spectrum of this metric graph by computing the zeros of this entire function. So our graph, the polynomial only depends on g, but the lengths come now. I evaluate pg on this line, e to the ikl1. K is now a complex number, but all the zeros are only going to be real because of this stability condition. So you look at the zeros with multiplicity. That's why I made the definition of the zero at the origin so that this statement would be true. So you now have a way of computing it. And so the things that are going to be immediately important are what is this polynomial, where is its zero set, and then how does this line intersect that zero set? The places where it intersects it, what kind of structure does that have? That's not obvious, but Lang's GM will solve that. All right, so the subvariety here, this roots of this polynomial, Laurent polynomial in this torus, is central to understanding this. So as I pointed out, and now we see why that happened, the polynomial, of course you can compute any given one easily enough. If you take the figure 8, you compute it, it turns out that the zero set happens to be 3 subtori. That's why it was a union of 3 arithmetic progressions. It's itself a subtorus. So the polynomial, when you compute it, factorizes into z1 minus 1, z2 minus 1, and z2 minus 1. So it's 3 subtori. And that's extremely unusual. That'll be a theorem in a second. There's another, the question is when these are irreducible is very important. And there's another case where it's not irreducible. My coworker calls it a watermelon, and it's what you see over there. It's that graph over there. The polynomial there factors into 2 factors. But other than that, the next theorem, the first theorem, which allows us to proceed, is that the secular polynomial factors into a factor qg of z times a product of these very simple things here, zl minus 1, ze minus 1, as you go over all the loops in the graph. So if the graph has no loop, there is no second factor. And the first factor is absolutely irreducible. That's the key thing. And this, if we're keeping away, we're assuming that we're not the watermelon. So that's not it. And then the second factor, and this is going to be extremely important to understand the subvarieties. It's very difficult to tell what all the tori sitting in the zero set are, but the biggest degree torus we understand completely. So there is no n minus 1 dimensional torus in any of these unless you are the figure 8. The figure 8 is the unique exception. And this is proved using some graph theory and some elementary concatenation of, contraction of graphs and following the factorization. It was conjectured by Colin de Verdier, who was studying something else, and it's critical to our input here. Okay, now let me state the main theorem and then show you roughly how you reduce it to this. So we have a metric graph, and I want to understand the spectrum of this metric graph, which is now not just a circle. Then the theorem is that the spectrum can be decomposed into a structured part and a non-structured part. The structured part, L1 up to L nu, are linear full arithmetic progressions. So in the spectrum, you're going to have a finite number of full arithmetic progressions, nothing omitted, full arithmetic progressions, L1 to L nu. And those can be determined effectively, because that yeah, those can be effectively, be precise about that. And then a part which is left over in this union, this is a disjoint union with multiplicity. So this is a complete description of the spectrum. And then there's n of x, which may be empty, but is only empty in the case of that figure 8. So the spectrum has this arithmetic progression part and this very interesting non-structured part, which we call n. If n is non-empty, which it will be except in one case, then we know it's asymptotic density. It's not just that it's non-empty, it's a finite number of points. It's a positive proportion of the numbers. And the main theorem about n, why am I saying it's got nothing to do with arithmetic progressions, and this uses the full force of the uniform statement, is that n of x intersect any arithmetic progression has at most a fixed number of points. That depends only on the graph. So there are no arithmetic progressions in the spectrum, in the non-structured part, which are bigger than some fixed number. So it's extremely far from an arithmetic progression. It's got nothing like an arithmetic progression. And moreover, the span, the Q span of the spectrum is going to be, of the non-structured part, is always infinite dimensional. And people were looking for a feature like this, as you'll see in a second. Okay, that's the structured theorem. It uses Lang, GM. Which happens when? Well, if all the L's are projectively in Q. So if you can scale them all to lie in Q, then we're in a periodic situation. N is empty, and that's a trivial case that you don't need this theory to understand. And the opposite extreme, if L1 to Ln are linearly independent over the rationals, then n of x is everything, and there are no arithmetic progressions. So those are the two extremes. In general, you can have some subtori. The Lang GM is what's responsible for this theorem, but it's not a vertical version. It's because when I intersect, I then make the subgroup generated by the intersection points, and that is already much deeper. At least, I'm not saying the theorem's deeper. What I'm using is deeper. Often you use a big sledgehammer, and there's actually an easy proof. I don't believe that there is here, but there may be other theorems you could use that are somewhat simpler. So that's the structure, of the additive structure, and it's the third application that I wanted to mention. Now, in this theory of quantum graphs, just like the sum of the point masses on the spectrum should be a sum of delta masses, it's always true that the sum of the point masses in the spectrum, its Fourier transform, is the sum of delta masses for a quantum graph. That is a beautiful theorem, I think first discovered by Smilansky and Kurasov, though Roth was writing something, not the same Roth, some other, Jean-Pierre Roth was writing something similar before. So every one of these quantum graphs gives me a crystalline measure, meaning the sum of point masses is a sum of point masses. What is the right-hand side here? Well, so delta function at the origin corresponding to Weyl law that you expected. But then what you have is a sum over all periodic orbits, and there are a tremendous number of periodic orbits because this graph is, even if there's no loops, there are an exponential number of periodic orbits. But what you do is if you have a closed orbit with an oriented cycle up to cyclic permutation, of course, then as you go around, you multiply. So this is what this SP is, the scattering matrix. As you go around, you multiply. Each time you go through a vertex, you multiply these S's, and when you come back, that's the coefficient S in front of the delta mass there. So in the case of a circle, you just have one way to go around, and that's why the Poisson sum's so easy. But here you've got many ways to go around. You collect all of those with the same length. It's a tempered distribution. The lengths are positive, and the set of positive linear combinations of the lengths is not a dense set. It's got at most t to the n values when t gets large. And the support of the Fourier transform of this measure is a sum of delta masses, and it's an example of a crystalline measure. You might think that this, let me just mention a beautiful theorem of Levin or Levsky about crystalline measure, because people are trying to classify these kind of Poisson summations because there's a Poisson sum that's connected with the sum over the primes and the sum over the zeros of zeta, and that clearly, what's putting all the zeros on a line must be in the back of your mind here. This theorem here says at least if you have a measure and it's a sum of delta masses and the measure is locally bounded and the Fourier transform is a sum of delta masses and is locally bounded, then it has to be an arithmetic progression or a finite union of arithmetic progression. So these quantum graph guys, except for the figure 8, are all exotic. They can't be because they are not, they're not arithmetic progressions. I proved that to you in spades by showing there are no progressions of a fixed length contained in the full set. So the Fourier, on the right-hand side, there's a lot of cancellation with those S's to make the thing tempered, and they give you these very exotic crystalline measures that Meir was looking for. Every graph gives them, but many more give them. So when we were doing this, we wondered, is this the only way to make them? Well, as long as you start off with a stable polynomial and make certain, and assume that P and that P iota was also destable, you can go through this construction and make a crystalline measure with exactly the same properties using Lang's GM. And there are many polynomials, and this is an important thing, that are known to be stable, not because they are determinants of something which is unitary. And the most famous one of those are the Li-Yang theorems in statistical physics, which are polynomials in several variables which are stable. And there's a whole theory of proving stable polynomials, and they're not all gotten this way. So this is a very rich class. The Riemann hypothesis lies somewhere else here. That is clear. Let me return. I have 3 minutes, and I will talk tomorrow about this other example. It's the basis of tomorrow's talk, but it's a vertical application due to Dubrovin and Matsako of Lang's GM. They didn't call it Lang's GM. They didn't use it. They needed a special case. But the theorem is so beautiful, I've got to tell you about it. So you all know that the Gauss hypergeometric function f(2,1) of z, alpha, beta, gamma, z, there are a finite number of those which are algebraic functions of z, and they were found by Schwartz by computing Riemann's monodromy and checking which of those have finite monodromy. Finite monodromy is equivalent to algebraic. And this comes down to reflection groups in the plane, and that's a beautiful classification of Schwartz. For many years, people were trying to understand what happened here. Painlevé, which come in 6 types. The hardest one, the only interesting one for us, and the most difficult is the Painlevé 6. It's a second-order nonlinear ordinary differential equation. It comes up in many integrable systems and in physics, even in relativity, in string theory. Anyway, it's some special function which satisfies the second-order equation that I've written over there. It's got 4 parameters, just like the hypergeometric. It's got 3 singular points, 0, 1, and infinity. The only big difference is it's nonlinear. So the monodromy group is not linear. But there's a theory there which says that if you look at the monodromy, which means you take some point, you take the right coordinates to measure what happens when you go around the cycle and come back, you'll get a nonlinear transformation. There's a theorem of Jimbo and et al., which says that if the nonlinear monodromy is finite, you algebraic function of z. So people wanted to classify all the algebraic Painlevé 6s, and this was done brilliantly, as I said, by Dubrovin and Matsako, and by those names that I can't in the general case, but that is very difficult to read, that kind of, they're from the same place, I think. Their paper's kind of interesting, and I don't know that it's been checked, but I had one undergraduate check most of it. So they have a list. The theorem is they give all the thetas finite list of the algebraic Painlevé. The problem boils down, I just want to say where it's got to do with Lang's GM. The problem boils down to understanding this nonlinear monodromy, which turns out to be a nonlinear transformation, in this case of a surface to itself, and you need to find all the finite orbits of this action. And it's nonlinear. And the action turns out to be in the right coordinates, at least if the first theta x, theta y, and theta z are all equal, to this simple action that I'm going to talk about a lot tomorrow. What's a Vieta move? You take x1, x2, x3 in 3 dimensions, to x1, x2, x1, x2 minus x3. That's a nonlinear involution, and you do that in each of the coordinates, and you take all the permutations with that. I'll call that the Markov group tomorrow, and I see that I'm running out of time, so I'm going to stop here. I'll just say that you need to classify all the finite orbits. And there's a very nice reduction to Lang's GM, which is you have a set of possible solutions to this Diophantine equation. This is how it's solved. And that solution, Lang GM, will allow you to parameterize those solutions. Everything's effective. It's vertical Lang GM. And from that, you then check which ones actually give finite orbits. And you have your finite orbits. And you've got this amazing theorem as to all the Painlevé 6s, which are algebraic. I've made an advert for tomorrow. I appreciate you all want to go trick or treat. Thank you.
Or any questions, I'd like to first announce that there will be a reception on the 4th floor of the center, common room department. And now take some questions.
Well, my one question is, yeah, you can't tell me there is no quantum graph. Then I'll be, then I'm finished. Or all quantum graphs are just this, yeah. They're very rich, and people study all aspects of them, and they had been asking about the structure of the spectrum. Can't hear you, what? Quantum tunneling, yeah, okay.
Yes, please.
Yeah.
Do you know any applications of the analogs of Lang's theorems outside of GM to either the Abelian variety or Schur variety case?
So I don't. I asked Peter, and he had some, but it was again to Diophantine analysis. So if you ask outside abelian varieties, so a torus will come up in engineering, and abelian variety a little less so. The Shimura variety, forget it. So the Shimura varieties, which are CM points, hard to imagine how you make another construction and then you need to know the solution. So if somebody does, I'm very eager to know that. To me, it's kind of, the way I faced it first was I needed that, I was trying to understand these Betty numbers. And I looked at Lang's book and I saw this conjecture and I thought it was unsolved. And it was, I was able to do this vertical version, yeah. Echo happened to be working quite separately on that. So the word is abelian there. By the way, if you take non-abelian covers, and you ask about the irregularity, there are all sorts of beautiful questions like a hyperbolic three-manifold, and you're going through congruent subgroups, how do the Betty numbers behave? Until recently, we didn't even know they switch on.
Questions?
Yeah.
Can you say more about the non-structured part?
I thought I said quite a lot. I needed that uniformity. So firstly, if you asked me what's the intersection of the set with an arithmetic progression, I can't even tell you what that is because it's not effective. I can just bound that from above. You can, okay. You can, and this is a beautiful, what Gaspard, and you can use some elementary ergodic theory on the torus to look at the consecutive spacing. So in this kind of quantum chaos world, that people are interested in the distribution of the spacings as you go through the spectrum. And that has a very easy answer. Because the codimension one subvariety where you're intersecting, and you're looking at how often you intersect, you can imagine that this, if you're irrational, or it depends what, let's say you're irrational, or L1 to Ln are independent, then the number of times you'll intersect can be expressed in terms of this subvariety in the torus and the Gauss map. And you can write down something very pretty there. It's not universal, so each quantum graph has its own distribution, and it's not random matrix theory. The conjecture there is that if the graph gets large in a suitable way, then it will converge to what's called GOE. So that's much easier, and that's what people do. This harder question, I can't say much more. Your question is, which I'm sure is true in many cases, are these linearly independent, or are they transcendental? Yeah, I don't know.
Other questions? I'd like to thank the speaker, and also there's a reception.